Thanks, Bertus. I'm just going to be very brief. I'm sure most of the people that's here is aware, know who you are, but for those who don't, I'm just going to give a brief introduction of who you are. Prof. Bertus Smith is Associate Professor at the Department of Geology at the University of Johannesburg, where he's been employed since 2008. His main research interest is iron and manganese in chemical sedimentary environments from both economic and environment point of view. Yeah, his interests include also applied mineralogy and early Earth environments. And yeah, Bertus, with no further ado, I'll let you talk about your talk and you can hit it off.
Okay, thank you, Conrad. Thanks for the introduction, and thank you also for the invitation to give this talk. So firstly, this is a talk I did give it last year at a Samera SGA workshop, which had to do with critical metals. And I think a lot of people, when it comes to critical metals, they'll talk about a lot of interesting, more obscure things that are needed in like capacitors and batteries, and lithium is also a big one as well. But I sometimes think a lot of the bulk commodities are also, forgotten about, and that critical metals are not always the new hot ones, but also some of the older ones on which our modern society has essentially been built. And then also that, as time goes by, these things will still be quite important. So we shouldn't just necessarily forget about some of these old fundamental ones. And yeah, I'm going to talk about manganese. This is a Northern Cape branch talk, and I think most of the people here at least know the Northern Cape province is quite a critical one with regards to manganese and manganese deposits and manganese mining. And I mean, it does have a history that's pushing almost 100 years, maybe not quite, but getting close to 100 years of manganese mining history in that region. So this is the title of the talk. It's Manganese in South Africa, a match made in history, a relationship for the future. It is going to do a bit of geology as well, but I also spoke to a couple of other people regarding this matter, and so there is also some other interesting information. And so you'll see there Nick Beekers, who unfortunately passed away now just over a year ago. He, of course, was my mentor on getting into research on manganese, at least from a geological point of view. Bjorn van der Heijden, who's now sort of starting to dabble a bit on the geometallurgy of manganese. He assisted a little bit. And then also Johan Kriek, who's a former manganese mining company CEO. I also had a chat with him, and he provided some pretty interesting insights as well. So here we go. So basically this talk will go and talk about the past, the present, and the future with regards to manganese. Of course, the timescales won't be quite equivalent, needless to say. So here we go, my talk: no manganese, no steel, no economy. So it's a one-slide talk that I'm giving, and I guess that's it, but not really. But it is a true statement. As things stand at the moment in the technology we have, the technology we use, we cannot have construction-grade steel without manganese. So it is, in essence, with that regard, a critical commodity. And we're not moving away from steel anytime soon with regards to construction. So no, it's not quite the end of this talk. So we'll go into a bit more detail here, some background on manganese as a metal. It's a sulfur fixer and a deoxidizer in steel. Maybe some of you already know this, but it essentially makes steel stronger. It makes it something that's better to work with, the workability. It also gives it resistance to wear. It helps with some anti-rust characteristics of modern steel. And for every ton of steel, you need about 4 to 8 kilograms of manganese. So yes, you're talking here about a ratio of about 200 to 100 to 1, somewhere in that ballpark between steel and manganese. But that 4 to 8 kilogram within every 1,000 kilograms is absolutely critical to make it work. There are other secondary uses as well, like cathode material in batteries. We'll come back to that, because everybody's like, but batteries are super important to the green economy. Yes, it is. But we'll chat about that again a bit later. As an oxidizing agent, they add it to rubber, glass making, fertilizer, ceramics, animal food. aluminium cans, all these things take manganese, and manganese is important in all of them. But the vast majority of manganese goes into steel production. So what about manganese and South Africa? So we're going to start with the past. There's a past that goes back from 3 billion years ago and onwards. We'll talk about the present, plus minus now. You see there plus minus 2023 because I gave the talk last year. I should have probably put 2024, but I put a plus minus there, so I feel I get a mulligan on that. And then the future, tomorrow until who knows when, with regards to manganese and the role it plays within South Africa. So the past, I always say the nerdy stuff. This is the stuff I'm super interested in. It's sort of the science where we try and tell about the past. Yeah, I always say geologists, we are biographers of the earth. We're trying to write the earth story. And manganese tells a super interesting story, especially with regards to old ancient surface environments. Now, from an economic geology point of view, within Southern Africa, there are more different manganese types. But within South Africa, the most important ones by far, it's the banded iron formation hosted or associated manganese deposits. But then also you get the karst hosted deposits, which also plays a slightly more minor role within South Africa. And these deposits are all Paleoproterozoic in age. They, although with the host rock maybe formed 2.5 billion years ago, the deposits themselves formed about 2.4 to 2 billion years ago. And then there are some overprints, probably a big one at around 1 billion years ago, and then a couple of more recent ones. If you go up to Namibia, there are some manganese deposits there, much smaller than the ones in South Africa, but they're about Neoproterozoic in age. They're associated with what's called the snowball Earth, where a lot of researchers think that essentially the Earth was almost completely covered in ice because you see glacial deposits very close to the equator at that time. And then essentially you seal the ocean off completely with ice, or at least large bodies of water. And when you seal the body of water off from the atmosphere, you essentially start making it anoxic. The oxygen starts getting used up. There's no new source of oxygen coming in, so you can dissolve large amounts of iron and manganese in that enclosed, restricted body of water. And then later, as the ice melts, you reintroduce the oxygen and you deposit a large amount of iron and even manganese in some of these deposits. Important in Namibia and maybe places like Brazil, not so much within South Africa itself. You also get some smaller oolitic and supergene manganese enrichments, and you get very recent hot spring-related enrichments as well in places like the Western Cape and so on. Now, with manganese, it's a very interesting element. It's got a very interesting chemistry. I always joke and say there's like a love-hate relationship with iron. Iron and manganese, both, if you're close to sort of neutral pH, they are dissolved in their reduced state, iron 2 plus, manganese 2 plus. And as you increase oxidants in the system, especially something like oxygen, when you get to iron 3 plus, manganese 3 plus, manganese 4 plus, they essentially become insoluble and they sink out of the water column. So what's interesting about manganese compared to iron has, it's easier to oxidize than manganese. So the pathways to oxidize and deposit it, there's a bit more room for interpretation. Whereas with manganese, it's very difficult to do that without free molecular oxygen and actually biology. Most of your modern day marine deposition of manganese has some sort of biological activity involved somewhere in the chain of events that leads to the oxidation and deposition of that manganese. And also, if you look at the Earth's history before what's called the Great Oxidation Event, which happened, some people say 2.5, some people say 2.2, plus minus 2.4 billion years ago, you don't see as much manganese enrichments in the Earth sedimentary record. It only really starts kicking in after that, probably related to the availability of oxygen, and also probably due to an excess of iron in the system. Because what essentially happens is, I don't know if you can see my cursor here, but this is called an EH-pH diagram. EH is oxidative potential, and black is manganese, red is iron. And as you go up in your oxidative potential, you'll hit that red line first. which is where you oxidize and deposit iron, you essentially have to remove all of the reduced dissolved iron out of the system before you can get to manganese, oxidize it, and successfully deposit it. So it is a very interesting element. And as I said, it's very hard to deposit and enrich it without first removing all your iron, and then also having some free oxygen available. And also interesting about manganese, where iron enrichments are not so common anymore, because iron is very quick to be taken out of solution at hydrothermal vents. Because manganese can go into solution at conditions where iron will still be oxidized, you can, in even more modern systems, get restricted basins where manganese can enrich. And often what you get there is sort of these figures C and D here. You can almost get like a little bathing model in modern systems where the water hits the sediment and it's just in that right spot for manganese to oxidize and go into the sediment. You'll get this band of manganese enrichment, like a little bathing around that specific body of water. For example, that is happening today in the Black Sea. But back in the past, sorry, I think I just hit something on my mouse that took us back a slide. Here you can see enrichments of iron through time. It reaches a peak about 2.5 to 2.4 billion years ago. And this graph is heavily biased because that massive peak there is the Kalahari manganese field. So this sort of global graph of manganese deposition through time is heavily biased by the fact that the majority of manganese we see preserved today in land-based deposits sits in this one, which is the Kalahari manganese field. But you can see that it does appear that manganese enrichment is like a little hangover that follows iron enrichment, probably because you have to take the iron out before you can start properly depositing the manganese. But there is interesting stuff here in South Africa and one or two other places, like in Canada, there's some examples as well, where we do see some isolated manganese enrichments prior to the Great Oxidation event. So a lot of people, myself included, believe that that means even before the Great Oxidation event, there was some free oxygen available, maybe not everywhere, but we're starting to speak like you had these sort of oxygen oases in some places where, at least locally in a basin or in an area, there was probably some photosynthetic bacteria producing local oxygen, and that at times just became enough that you could draw down, deposit all the iron, and go over into some manganese deposition. But it is very tough to do, because even if you're oxidizing manganese in an ocean, if that manganese falls back into some water that has a lot of dissolved iron, it'll back react with the iron, oxidize the iron, reduce itself back into solution. So even in these ancient systems, even if you had manganese oxidation, often it would just get recycled right back into solution. So before the GOE, it was very hard for manganese to get properly deposited and built up and preserved in significant quantities. Also important to note, these manganese buildup, they're not economic. They're isolated, they're not big. So generally, from an economic point of view, they're not so important, but they are interesting in the story that they tell of the Earth in the days leading up to when it seems oxygen really started taking over. Now, here we talk in the past, we talk about the Kalahari manganese field, which is hosted in what's called the Hotazel Formation. It's very close to the top of the Transvaal supergroup in the Griqualand, bigger Griqualand West region of South Africa. This is the big one. It's estimated that 70 to 80% of the world's land-based manganese is sitting in this one deposit. Originally, it was thought to have deposited about 2.2 billion years ago, but now we're pretty sure it's more at 2.4 billion years ago that it was deposited. The first manganese enrichments were discovered at Black Rock, where the only outcrop of these rocks occur. Most of it is covered by the Kalahari sands, and that was in 1907, and they started mining it in about 1936. But before this, they had already started mining the other deposit types that we get in what I'll mention later, the Bosmasburg manganese field. But this is the big one from even a global world point of view, because as I said, there's 70 to 80% of the world's land-based manganese sits there from what we know, unless they discover another big deposit somewhere. I say land-based because we do know there's a lot of manganese sitting in ferromanganese nodules on the ocean floor on Earth today. And if you add all that up, it will dwarf what we see on land. But for the time being, there's no big prospect of mining those. So there we are, a little block here, Northern Cape Province of South Africa in the old Kalahari. And if you zoom in there, it's a very boring looking map. A big reason why it's so boring, the geology is a bit more straightforward, at least from a sedimentary stratigraphic point of view, but all of this is also sitting underground, mostly. It's only sort of in the Black Rock region up there. As I said, the only natural outcrop of the Hotazel Formation occurs. Down here, the whole thing is called the Kalahari Manganese Field, but it's got certain smaller deposits. The big one here is the main Kalahari deposit. Then you get the Avontuur and the Leinster deposit. The vast majority of mining occurs here in the main Kalahari deposit towards the south. Now, the Kalahari Manganese Field, there has been a bit of a lull, although it's always an interesting topic. There's been work on the Hotazel Formation and the Banded Iron Formations and so on, but there is a bit of renewed interest in trying to better understand how exactly this deposit formed and how it was deposited. There are some older ideas by other researchers that have been around for a while, but also a lot of newer measurement techniques, geochemical measurements and isotopes are starting to become available. But in my experience, the more information becomes available, the more contradictory a lot of these things become. But here, for example, is the old Nick Bierkes model, very nicely redrawn for the 2013 Kencross and Bierkes book, which about the Kalahari Manganese Field. But now also newer research is coming through. There was a 2023 paper from researchers at Rhodes University that also proposed certain ideas about how it could have formed and what exactly happened. But it does appear there's at least consensus that you're either dealing with an early great oxidation event or pre-oxidation event buildup of oxygen. So general consensus is you probably need quite a bit of free oxygen to have formed this deposit. What is interesting, though, for example, for me, if you look at a lot about manganese and you're looking at its relationship with iron, let's say the iron and manganese, it's dissolved, it's pushing from the deep water to the shallow water to the coastline. You would expect in the deep water, you have to remove your iron. And once the iron is removed, you deposit your manganese in shallow water. And that is what we see in certain manganese enrichments, like in the Pongola supergroup and other places as well. But for example, in the Kalahari Manganese Field, you get deep manganese. If you look at that drill core, very sort of massive little lamina in there, but it's devoid of any active sedimentary structures. And then you look at this because these manganese beds are interbedded with iron-rich beds, banded iron formation. And you look at that there, and the banded iron formations have got silty and sandy beds. There are little wave ripples in there, low angle cross bedding. So clearly this was deposited in shallow water. So already just by looking at the core, you're sort of going and you're like, you know, WTM, what the manganese, you know, what's happening here, what's going on. So I think there's a lot of room for further research, and there's a lot of interesting ideas slowly emerging. And one of our UJ post, a PhD students also has a nice paper coming out in South African Journal of Geology, for example, on the Avontuur deposit, which is further north. And they were also seeing a whole bunch of weird minerals that we don't see in the main Kalahari deposit. So I think there's still a lot of interesting stuff to do there, and a lot of stuff we don't yet quite fully understand, at least from a geological telling our fairy tales point of view, because that's the fun and the frustration of geology, is you're looking at very old things, and you're trying to measure the characteristics of these very old things. But if you boil it down to it, there is quite a bit of room for interpretation at times. And then we get the Bosmasburg manganese field. So the host rocks are older than in the Kalahari manganese field, which are the carbonates of the Campbell-Rand subgroup. But what people think here, although there as well, I think there's room for research because you get different ore types in different parts of the Bosmasburg manganese field. And some of these ore types, there is still some room to better understand how they formed. But in very, very, very simple terms, it does appear that there's a lot of karstification, old, recent, yes, but it appears like at over 2 billion years ago, massive cave building events, karstification, and you're essentially dissolving hundreds of meters of dolomite and calcite in the carbonate rock, and the manganese that's in small amounts in these carbonates are residually building up in these pockets here, in these karst sort of landscapes. And it's also called a WAD type manganese deposit, which is short for weathered altered dolomite. And then you get essentially what looks like a lot of these deposits, when it's been mined out, you literally see residual dolostone pinnacle fields sitting in the deposit. That it literally seems like the manganese settled down and residually enriched in these dissolution cave and sinkhole structures. So this one has been mined for longer than the Kalahari manganese field. And there is still quite a bit of active mining there, but it's at a much, much smaller scale. And the reserves here are also a lot less than what you see in the Kalahari manganese field. So there you see it right there. And that's plus minus where that Bosmasburg manganese field sits. Now we're done with the past. So the nerdy stuff is mostly over. And in some broad terms there, I told you in South Africa, big boy Kalahari manganese field, 70 to 80% of the world's manganese reserves. Now look at this here and you see top manganese ore producers. I think this is 2022, 23 numbers plus minus. And you'll see there South Africa is by far the biggest producer of manganese ore at about 7.2 million tons, followed by Gabon, Australia, China, Ghana, India, Brazil. Gabon's strong, Australia's strong, but South Africa, you can see there, not quite double, but almost double the production of Gabon, more than double the production of Australia. It does make sense, especially if you consider South Africa seems to have 70 to 80% of the land-based reserves happening. Now we look at manganese. Where does most of it go? It goes into steel production. And there you can see now the top steel producers. By far, it's China, followed by India, Japan, USA, Russia, and so on. And here you can see the top steel consumers. Please note, though, this number will be a bit strange because it's per person living in that country. So, of course, advanced countries with lower populations will have a bigger per capita consumption. But either way, if you look at these three columns of manganese ore production, steel production, and steel usage, you'll see that there's not a lot of correlation here. There's quite a bit of a disconnect. And I mean, it's almost like, you know, what's quite going on here? Why all this disparity and how these things don't line up? And I mean, as geologists, I'm sure most of us geologists, we already know where the commodity sits and where it's needed is often just not the same. And that can lead to a lot of interesting economics and social politics and so on. And with manganese, that is very, very clearly the case. Where it sits and where it's needed, these places don't align. So also interesting about manganese mining is that the profit margins of manganese mining run at much higher margins than, for example, the manganese alloy and steel production industry. Manganese mining can run at margins of up to 1,000%. Whereas steel making and manganese alloy production runs at 2 to 3% margins. So it does seem from a profitability point of view as an investor, you want to invest in the mining. That is the greatest potential to bring you return on your investment. Now, yeah, sure, it looks like that. But of course, as always, these pictures are a little bit more complicated. And the big elephant in the room here is you can invest in manganese mining as much as you want. The industry that uses it runs at low margins. So you can't really have the one without the other. So it is quite complicated. Now we said manganese mining looks like the place to invest. So let's look at where we get manganese deposits on Earth. And what's quite shocking is that you can basically bring it down to 5 places on Earth that we know about which pushes the needle on manganese mining and manganese ore production. 5, how many other commodities do you know like that? And I'm not even talking about countries. I'm talking about deposits. Like you can go about iron ore, for example. Yeah, Australia's big on iron ore. Brazil's big on iron ore. South Africa is also in the mix, couple of countries in the mix. But this is coming from different deposits. These are single deposits in specific countries that overwhelmingly control manganese ore production in the world. So you're now thinking, manganese mining can potentially run at much higher margins, good place to invest, get return on investment. So as an investor, you're great, but for manganese, options are limited. So let's look at these options. Here we get Azul that sits in Brazil. You did see Brazil did feature a little bit on that manganese ore production, although they have slipped down quite a bit of the rankings. And there's the Azul deposit. Problem you have, it's almost mined out. And that is also probably to an extent why Brazil's slipping down in those rankings on manganese ore production. Let's look at the next one. The next one is Groote Eiland, north of Australia. Interesting deposit. It's fairly young. It didn't form that long ago, so it's geologically fairly recent, and it's literally an island rich with manganese ore north of Australia. Now, what's happening there if you're thinking of investing? Well, guess what? That's also almost mined out. So Australia currently sits 3rd on manganese ore production. They'll probably gradually start slipping down quite significantly. Next one, Comilog in Gabon. Big deposit, lots of investment there from Eramet, which is a French company. However, here there's a couple of issues. So, for example, there was quite a bit of socio-political unrest in Gabon, where there was a military coup that happened, where the government was deposed. However, that does not seem like it affected the manganese ore production too much in this instance. But a lot of this already has French investment between the French mining company and the Gabonese government. So there, the room for flexibility, there's potentially some challenges and caveats there. Then there's another interesting, fairly big manganese deposit, which sits in Kasenge in the Democratic Republic of Congo. However, looking at that satellite image there, where it sits is you're sitting essentially almost halfway between the east coast and west coast of Africa in an area that is not logistically well developed. So as it stands, there's basically no mining happening there, and it would take a lot of upfront capital to get that up and going. And then that brings us to the Kalahari manganese field in South Africa, number 5 on the list, and as we know, by far the biggest single deposit of manganese on Earth. And there's an investor who's now starting to think, ooh la la, this could be good, this could work for me. And there is definitely potential there. So in the Kalahari manganese field, this is where most of South Africa's mining is happening, and this is also where most of the world's manganese ore is coming from. Low-grade ores are mined in the southern Kalahari manganese field, whereas in the northern part of the main Kalahari deposit, up here where you see the darker colors, there are some high-grade ores as well. But because the tonnages are so high and the grades are relatively consistent, they can mine these low-grade ores. These are essentially primary chemical sedimentary rocks that have essentially not been changed other than a bit of diagenesis since they were deposited. And that is mined as it is for the vast bulk of the manganese ore in this region. There, as I said, in the Postmasburg manganese field, there has been some renewed interest in mining again, but it pales in comparison with what's happening in the Kalahari manganese field, where South Africa produces approximately 36% of the world's manganese ore, mostly from this one deposit. So it is good, it looks great. South Africa is well positioned, high reserve availability, there's variable quality, but it's also low phosphorus, which is good. Barium can sometimes be a bit high, but not quite a deal breaker. And as I said, 70%, although some people put it at over 90%, I guess it depends how optimistic you are with the information at hand, of the world's global manganese reserves on land, assuming we're not going to go start digging up the ocean floor. But for example, now we're talking about manganese ore mining versus steel production. Now, there have been smelters in South Africa that have produced steel and also manganese-related alloys. However, a lot of them have been shut down in recent years, a lot of it due to load shedding, but also because on the global stage, it can be very hard to compete, especially against countries like China or India, countries that just do more for less. So in South Africa, the shift has definitely moved towards just mining the ore and exporting the ore. That is the main focus at the moment. So as I said, for steel production, the manganese can be alloyed as a ferromanganese or as a silicomanganese. I'm not an expert here so much on the geomet of manganese. I work more on the actual geology. And unfortunately, I don't think Bjorn's here today to answer these questions. But just a little bit about a little diagram there to show you what needs to happen to the manganese and towards the getting the steel produced. And most of that steel production is driven by China. And this is important to take into account because during the COVID pandemic, for example, China definitely had much stricter lockdown policies. And in that country, when the government shut down to try and avoid the spread of the virus, it shut down a lot of things. We know this. There were chip shortages, so you couldn't buy a car or you couldn't get a phone for a while. And I mean, if they just shut down, they stop producing steel. And if they're not producing steel, they don't need manganese ore. So what's going to happen to the price of manganese ore, for example? And then which country's mining economy then stands the most to lose from it? But at the same time, if steel production's high, who stands to gain the most of it? And then earlier I did mention that manganese has also been used in the cathodes for batteries, and batteries are critical to the green economy. But less than 2% of manganese is used for that. And manganese is not the limiting thing there. It's the lithium. So lithium will probably be the main thing that controls battery production and the battery part of the green economy. So manganese is still where it's important is steel production. And I mean, even if we're going to a green economy, if you want to build solar panels, if you want to build wind farms, if you want to build hydroelectrical power, whatever the case might be, steel is still critical in building that infrastructure. So that is at least where people see the main importance of manganese for the foreseeable future. So growth in the steel industry combined with high reserves in South Africa will keep South Africa as an important cog in the global manganese supply chain. Now, at the current mining rates with the current mines that are developed in the Kalahari manganese field, though, in about 20 years or so, those deposits will be mined out. And then it's only, but how's that possible with South Africa having over 70% of the world's manganese production? Now, if you look at where they're mining in the Kalahari manganese field, a lot of these mines tend towards the eastern part because the deposit is dipping to the west. So they're mainly focusing on open cast mining in more easily accessible areas, although there are mines like Gloria and Nshwaning, Assmang mines, which have sunk shafts and are mining underground. But some people estimate if they're willing to now go and, for example, the top is Mamatwan mine, and the bottom there, I think that's one of the older Assmang mines. I think it's in Nshwaning. But if they move underground, they're willing to mine some of the deeper seated reserves. They're estimating that this deposit could supply at current usage rates the Earth's manganese for the next 5,000 years, according to some estimates. So there's no doubt it's there, and there's more than enough manganese there. So that is not going to be the challenge so much. And I mean, even if South Africa, these easy to get to deposits start running low and the manganese ore supply starts going down, probably the money will be there and the interest will be there to invest in these deeper mines, to mine these deeper seated reserves. But very important, and this is something I learned from Johan Kriek, former manganese mining CEO. This manganese mining is a non-elastic business. There's not a lot of room for adjusting your business plan. It's completely dependent on the steel industry as things stand. So what the steel market wants, it wants. So if the steel market is not making new steel. It's not going to need manganese ore. Most manganese ore goes into steel production. So what the steel industry is doing, and this is this industry that runs at these low margins, if that gets affected, it has an immediate knock-on effect on manganese mining, manganese ore prices. So you as the manganese mining company, you're like, please, sir, I want to supply some more from, I don't know, a very old reference here, the movie Oliver. You not want more porridge, you want to give them more manganese ore, and then the steel making industry will just say, no, we don't need it, too bad. So that is a bit of a reality and a bit of a risk that the manganese mining industry is exposed to. So some businesses are integrated. I mean, ideally in a system like this, you would want full integration, that the company making the steel is also the company mining the manganese. But as I said, where manganese is made and where the manganese reserves sit, not even on the same continent in general. So where these companies are integrated, though, what would happen is if there was some sort of downturn in their business and steel making does poorly, they'd ramp up the mining facet because the mining has higher margins and it looks like you're more profitable. But in the big scheme of things, what you then do is if the steel making is in downturn and you temporarily increase your mining to get more money in, what do? You essentially push down the price of your own commodity by oversupplying. So that's also a bit of a reality there. So the economics of this will have to be very carefully considered, and at the moment should be very carefully considered. So manganese mining is a highly concentrated industry, but the making of the alloys is a very fragmented industry. So having these two working in some sort of happy equilibrium can be very hard to do. And of course, it's obvious that within this value chain, South Africa's role will be in the mining. And that's where things need to be very carefully considered. So in South Africa, and I mean, this is something Johan Kriek mentioned, and of course, the reality is very different. Different companies have their deposits, they have their mines, they've got investors to take care of. But if you would be able to look at it more pragmatically and more holistically, you would want to avoid oversupply and avoid the collapse of your ore price. So maybe in future, a bit more coordination and communication would be needed, because even if a mining company then decide they're going to try and corner this market, the success will only be temporary, because at some point it always inevitably, even if temporarily, leads to a ore price collapse. And another big issue that I haven't mentioned yet is the logistics in South Africa. South Africa's infrastructure is not in a great state. We're always hearing about the issues at Transnet, for example. And of course, then what was supposed to happen is there's a railway line from the Kalahari manganese field and from Bosmasburg down to Port Elizabeth, but now people aren't getting capacity on the trains. So now they're shipping the ore down with trucks all the time. And of course, we all know here the classic natural occurrence, a very common occurrence, the classic Potole slagate. I think that's the scientific name of this occurrence here. Apparently, it's only extinct in parts of the Western Cape, but otherwise it's flourishing. And here we've got it, potholes and bad roads, and trucks are probably not helping that along. So that's also something that needs to be considered within South Africa's role, because what's the point of having all these beautiful mines and pulling all this ore in the ground when you can't get the ore to the harbors to get it to the steel manufacturers? So that would probably also need quite a bit of improvement and capacity building going forward. Now, what about steel and its role in the green economy? As I said already, it is probably the main commodity still used in this transition. Not just that, steel is, and this is another thing I'll chat about briefly, steel is also the most recycled commodity in the world. In 2021, about 840 million tons of steel has been recycled. Now you can go and say, but so why would manganese mining still be important? Why would iron ore mining still be important? Why is steel production important if it's very clear this thing is being recycled at a massive scale? Well, for people who have solar, of which I'm not one at the moment, and that's how you know people have solar, they tell you, is that these panels have a lifespan of about 5 to 10 years. So whatever things are used in that panel, or even these wind turbines, that commodity is locked up in that thing being actively used. So if it's actively being used, it's not available for recycling. You can only recycle things that have broken down or have been discontinued, or have to essentially be broken down and then recycled into something new that then again locks up that commodity within its cycle. So if you look at recycling, this is different things: plastic recycling, paper recycling. There you can see computer parts recycling. All of these recycling graphs have something in common, and that is this: up, down, up, down, up, down, up, down. There's a cyclicity to recycling because of what I just explained, being that things get locked up and used for a certain amount of time. How long depends on the nature of the commodity and the nature of the products in which that commodity is mainly used. So the issue here, though, is that the usage of these commodities don't do these cycles. The usage that is generally more consistent. So as things stand, mining is still required. Maybe not at the same scale as previously as recycling improves, but it's probably needed to try and pick up these little dips. Otherwise, the production of these products would also have to try and start following these cycles, which in itself will produce a whole new set of problems. So it will need to continue for the foreseeable future. There, nice, beautiful picture of Sishen and also one of the manganese deposits in the Kalahari manganese field. You actually see the late Prof. Nick Bierkus down there looking at the manganese ore, and this will still need to go and play a part in the future. And as long as steel production, not recycling, but new steel production happens, manganese will have an important role within that. And as things stand, it means South Africa's economy and mining and export will play a big role in that. So yes, recycling will become more efficient, and the dream is that it plays a larger role in the future, but it will probably keep on sticking to this periodicity, these up and downward cycles. So that is important to mention, because if I didn't mention it, maybe someone would have a question about it. But please note, as it works at the moment, recycling does not in some way suddenly mean we don't need to mine, because that's just not how the economy and the production of these products work. And then what about deep sea manganese deposits? Now, people are looking at these, but quite often they're rather looking at them for base metal contents, because often these things can have quite a bit of copper and nickel and other base metals in it. But as things stand at the moment, it does not seem that it will in any way supplant the current land-based manganese ore production. But we'll see what the future does. And then you can also ask, is it a good idea to dig up the ocean floor? I don't know. I'm not an expert on these deposits. But from what I've heard, they're not really considered a big game changer just yet. So just to conclude here, bring everything together, because I spoke about a lot of things, past, present, future. So something major happened 2.4 billion years ago on the western margin of this continent called the Kaapval Craton, on which South Africa sits today. And this thing led to the deposition of the biggest manganese deposit we know of. And that 2.4 billion year ago event now today places South Africa in some way at the forefront of steel production. So at the moment, South Africa is the top manganese ore producer, and it also seems from an investment point of view, this would be the best place to invest in manganese mining. But there are some major caveats, and some discipline and coordination would be needed, like improvement in South Africa's infrastructure, avoiding overmining and oversupply, thereby driving your own price down and collapsing your own industry. And then, of course, as time goes by, to take recycling into account as well. And that's the end of the talk tonight. Thank you very much for giving me this opportunity and for the invitation. And these are the acknowledgements, of course, the people who assist with funding us to do our research and, make get us to be able to do our live out our passion and research all these very interesting things. So this is now the time where either questions or people can tell me how wrong I am or whatever the case might be. As I said, my real expertise is more on the geology of it all. But I did then go out and chat to a couple of people, and honestly, yeah, it was some very interesting conversations and some very interesting facets to manganese and South Africa. So thank you, everybody. Conrad, if you want to take over as a chair for the question, although I guess I can handle it as well.
You can, Bertus. Thank you very much for a great talk. Yeah, it's open for questions.
Thanks, Bertus. Firstly, may I just say thank you for finally explaining what WOD is. That is a definition used on the mine or in our company quite often, and it's the first time I've actually gotten a definition, so thanks. But I just wanted to know, what are the sort of typical manganese mineral textures that you see in the Kalahari manganese field versus, like you said, that WOD that you would typically expect in the Portsmouthburg?
Okay, that's a super interesting, complicated question.
Okay.
So
yeah, because context, I work at Kolomela mine, so I'm trying to relate this to the iron deposits that I'm used to and seeing.
Yeah, I completely that's a very interesting question, because when you look at these iron ore deposits, you get your typical brecciated, laminated, massive conglomeratic shaly ores. Everything is hematitized. It's almost 100% hematite. And then you get these different textural varieties of the hematite that are probably pseudomorph replacements of older iron minerals. Now, with the manganese, if you talk about the bulk of the ore in the main Kalahari deposit, it's referred to as braunite lutite. So lutite, it's a chemical sedimentary rock that's massive, that's not well laminated or banded. And then braunite, people want to call it a silicate, but it's actually a manganese oxide with a little bit of silica in the crystal structure, but it's overwhelmingly manganese oxide. And then it's a very fine-grained rock with a lot of braunite in it, but also in the cement, but then also in little textures that are sometimes known as lenticles or little ovoids. You get quite a bit of manganese-bearing carbonate, like manganese-enriched calcites, kutnohorites, not really rhodochrosite in your primary ore. So essentially, it almost takes on the texture like a banded iron formation, but instead of iron-rich minerals, you get manganese-rich minerals. And because the formation of the braunite incorporates silica, where banded iron formation is more than half of it is quartz or chert, these manganese ore contains almost no quartz, because in the diagenesis, the silica was taken up in the formation of the braunite. So that would be your braunite lutite, although some of the information we see coming from the Avontuur deposits, they're actually a manganese silicate lutites. Which that still needs its own explanation at some point. When it comes to the higher grade ores, like you see at Vessels, there the textures have been significantly altered because you're getting a residual enrichment and a leaching out of other things. And then also there's a massive overprint, and then you start getting more manganese enriched oxides taking up similar hematite and magnetite structures. Then you're talking about Jacobsite and Jacobsite, Bixbyite, and things like that. And then the textures do start getting more messed up. A lot of the carbonates are gone, and you no longer see these little lenticules and ovoids. That's been completely obliterated. And they think that's a hydrothermal or a hypogene overprint that might be related to the tectonics of the Kais-Namakwa orogenic event. Then Portsmouthburg, those ores are very complicated because they're essentially these residual enrichments, and they're your mineralogy. I would say I haven't done as much work on those, so I don't know them as well, but they will also get a weird variety of more oxidized manganese minerals. Also, the fact that manganese occurs as 2+, 3+, and 4+. Means you get a much wider variety of minerals than you would get in iron ores and banded iron formations. So I would say, there's texturally, you might see some similarities, but mineralogically, there's big differences between the individual manganese ore types, and then between manganese and iron ore, massive differences. So I hope that sort of answers at least some of your questions. But there's very good papers and dissertations and theses out there describing these things in more detail. So you can always email me, and I'll pick up on a couple of these things and send it through. But it also depends on what the focus of the paper was. If it's a more paleo-environmental focused paper, it will cover more the lutites. Oh, and I must also note, there are some portions in the Kalahari manganese field where you get more like Jacobsite-enriched lutites as well, where it does appear that you could also get these more oxidized minerals as early diagenetic phases as well. But the bulk, the most common one is more what they call the braunite lutite.
Awesome. No, thanks, Bertus.
You're welcome. Conrad, did you have your hand up or did you give up?
It's still up. Thanks, Bertus.
Okay.
So my question is a little bit on exploration and other deposits. So from the sounds of it, the supply meets the demand, or more. The supply is more than the demand almost. So I don't see that there's a real big push to find new deposits, to find another Kalahari manganese field. So
that's the thing. The only reason why that would happen is maybe someone thinking they can corner the market, that they can produce the need for manganese ore in a cheaper, more economic fashion than what's happening in the Kalahari manganese field.
Well, then you'll have to find another Grote Eiland, I guess, which is very close to China, just almost
exactly. And and
so,
I don't know what the prospects of that is at the moment. It doesn't look promising.
So what I'm thinking, the only other place probably to find an extension might be Botswana and Namibia. I don't know if in the Transvaal there's any correlatives.
No, unfortunately not. The big frustration of it all is that they really have not found. There's some, even within the Griqualand West region, if you look at the lateral correlative of the Hotazel formation, it's the Beaumont formation, and it has no manganese. It really looks like this was not, it's not like what you see in these iron formations, the Penge, Hammersley, the Penge, Brockman, Kuruman, Griquatown iron formations, where it seems like you had this banded iron formation deposited across both these Australian and South African continents. It's really starting to look like this was something much like, almost like a Red Sea style deposit. So,
unconformity maybe that cut out some of the stuff.
Yes, that as well, sure. But the fact that there's a preserved correlative with no manganese, and it's just outside Postmasburg, which is not that far away, already spells a bit of doom. And as you said as well, the issue you've got here is that whole time period for the Hotazel appears to be missing from the main Transvaal basin. And it also does not appear to occur in the Kanye basin. So in the Transvaal basin, that's missing. People think that might be a structural unconformity or some big, from the Penge all the way almost down to like the Deutschland. There's nothing there. There's a gap of over 100 million years. And it's exactly in that time period where the Hotazel occurs in the Griqualand West region.
So not another Kalahari manganese field in Southern Africa?
It doesn't look that way. And there are places where people think, oh, but it should be there. But you must also now remember you've got the Priga-Magara unconformity, which took out a lot of geology. That thing erodes. That's the one it erodes all the way down into the carbonates, and you get the Postmasburg manganese field. That thing cuts across everything: Campbellrand, Kuruman, Griquatown, Kugas, Maganyeni, Ongeluk, Hotazel, Mooidraai. It cuts out a lot of those things. So yeah, you're also probably looking at a case that maybe there was more, but probably a significant portion was also removed by erosion.
Thanks, Bert. That answers my question.
Hello, thank you, sir, for the presentation. I just wanted to ask, with regards to the shadow zones in the KMF, the unconformity in the Transvaal Griqualand West Basin looks as if it's on top of the Mooidraai formation. So in that KMF area where we don't have the Mooidraai formation, is that unconformity on top of the Hotazel formation? That's
Yes,
correct.
so yes, there's two unconformities developed. The Kalahari and the Pre-Khamagara. There's actually, even in the broader geology in the area, there are further unconformities. But the Pre-Khamagara is a big one. And where it cuts into the banded iron formations that sit interbedded with the manganese field in the Hotazel, it develops scission-like high-grade iron ore. So what people don't always realize, a bit of a history lesson, is that they started building the steel smelters out in Pretoria. And a lot of those things were getting its iron ore from oolitic ironstones that sit in the Time Ball Hill. And even some that you can get in other things as well. But these oolitic ironstones were being used to feed the smelters in Pretoria. And when that ran low, they actually sent high-grade hematite banded iron formation hosted ore from the Hotazel area to supplement the smelters in Pretoria. So they only started mining scission in the late 1950s. So the first high-grade iron ore that came out of the Northern Cape to be used in South African smelters actually came out of the Hotazel formation. And that is where this Pre-Khamagara unconformity cuts into the BIFs that are associated with the manganese beds in the Hotazel. So you ask a very good question. So that Pre-Khamagara unconformity, I mean, a lot of places, you don't see the moidra in the drill core. In a lot of places, even, it cuts through the whole upper half of the Hotazel, and either the Pre-Khamagara, even the Dwaika, which is also a big unconformity, and the Kalahari unconformity can all be cutting down quite significantly into the Hotazel formation. Yeah, Musari Nkosi here talks about the Langdon Annex discovery in the 1950s. Yeah, that's a deposit that's been mined out that sits just to the east of the main Kalahari deposit. Thank you for all the nice comments. I really appreciate it. Thank you for those of you that might have called out inaccuracy in my talks for not embarrassing me on a public forum. I appreciate that as well. And then thank you everybody again. Loni Conrad for inviting me. I always enjoy interacting with the Northern Cape branch.
Thanks, Bertus. Appreciate it.
Thanks,
Absolutely.
Bertus.
Thank you,
Thank you.
everybody.
Thank you. Have a good one. Cheers, everybody. Bye.
Bye, everybody.